it is visible.
Yeah, so okay, welcome everyone to our second session on OpenMP programming. So let us first of all recap what we saw in the yesterday's session. So in yesterday's session, we saw what why do we need something like OpenMP, and what is the need of having multi-core systems and so on. I mean, what was the motivation for multi-core systems? Why did we have them at the first place? So we saw a bit of motivation, then we saw the classification of the parallel computers, and we saw different kinds of parallel systems that we have today. And then we later saw uh, how we can go about writing the parallel programs at a very high level, right? So what we saw was how we can do task parallelism and how we can do data parallelism. And in general, we saw that our program can have both task parallelism as well as data parallelism. And towards the end, we also saw that the issues that we might face, the complexities that we have while writing the parallel program. That is, we might need intercore communication, then synchronization, and load balancing, and so on. Okay, so that's the brief overview for the previous session. So in today's session, we'll be looking into the how we can how the parallelism works in OpenMP. So that is first thing that we'll see. Then we'll see what are the pragmas and runtime routines in OpenMP, and basically what are the constructs in OpenMP. We will see them, and later towards the end, we'll see this classic HelloWorld program. Basically, we'll write the classic HelloWorld program in OpenMP. So that is the outline for our today's session. So with this, let us start. So first, before I start, do anyone have any questions from previous session? Just to check. Quick check. Yeah, please go ahead. Vivek, please go ahead.
Um, so, thank you for having me here, sir. So sorry for redundancy, but I missed a bit of the starting portion of class due to internet issues. Could the
Yeah.
materials be shared so that I can go over them?
Yes. So recording and chat are already shared. I'll share also the slides. I'll upload it in the same Google Sheet that was circulated in the Google group. So I'll add the slides as well for today's as well as yesterday's session.
Thank you so much, sir.
Okay. Okay, then if there are no other concerns, then let us start. Just give me a moment. Okay, let us begin. So yeah, so this thing we saw yesterday, right? Okay, let me just remove this. Yeah, shared memory programming. What is shared memory programming? We saw in the yesterday's class, right? So in shared memory systems, we have RAM that is shared between all the cores, and that is what is the shared memory system. But the point here is that the point here is that our system, our application that we write, the program that we write, should be able to take the advantage of this multiple cores. So, okay, so what do I mean by that? So let us go back to our whiteboard and see what I'm trying to say when I say that our application should be able to take advantage. You just give me a minute, I'll share my whiteboard. Okay, so I hope that the whiteboard is visible. Yeah. So when you write a simple C program or a serial program, what will happen is that you have a multi-core system, right? Your laptop is, it has multiple cores, definitely. And the thing is, so these are the cores of your system. And this is the RAM, right? So this is what is our shared memory system. This is RAM. And let us say that you have this secondary storage, which is your HDD. And so the point that I'm trying to derive here is that let's say you have some simple C program, let's say hello.cpp, C++ program you have. It must be residing in some secondary storage, right? Unless you start running that program, it is in secondary storage. So your program is in the secondary storage. You compile that program using G++ hello.cpp. Your program is still in the secondary storage, but when you do ./a.out, your program actually comes in RAM as a process. So it now becomes a process because it is program under execution. So your program is here now in the RAM, in some part of RAM it is sitting, and it might have some stack and heap and all those things which a normal program have. And so the point that I was trying to say here is that your program P1, if it's a serial program, then what will happen is that it will run on a single core, right? On just one core, it will utilize just one core. So by default, any program that you write, it won't make use of this multiple cores that are available. It will just be running on one single core of your system. So this is the thing that I was trying to say. So okay, let me go back to the slides. Yeah. So the thing is that your application should be able to take advantage of this multiple cores, but writing a serial code won't work here. Your program will run on just one single code, which is single threaded execution. Okay, so to mitigate, to address this, what the developers thought of doing is that they created this framework called as OpenMP, which is parallel programming API for shared memory system, as we saw yesterday. And so using OpenMP, you can use, you can write C, C++, and Fortran programs, which can basically run on multiple cores. And yeah, that is what we are going to see. So C, C++ Fortran developers can create multi-threaded applications using OpenMP. And basically you will be able to it enables you to divide the computation among n cores. So, okay, now let us go back and see what will happen when you try to execute your code using OpenMP. When you are using OpenMP. So let me go back to here. So in this case, what will happen is that we'll have the same program, hello.cpp, but this time you will be adding some OpenMP constructs in it. We'll see what these constructs are in this today's session. But yeah, we are adding some OpenMP constructs, and we are telling the C++ compiler explicitly that, the C++ compiler is is an extended compiler which knows how to handle the OpenMP construct. So this we are telling the C++ compiler explicitly that there are OpenMP constructs in my program. So please look into them when you compile my code. So when you do this hello.cpp, when you compile it like this, G++ minus app OpenMP hello.cpp, your program will generate a binary similar to how it generates .a.out. So basically, what will happen is that again you'll have this process which will be there, which will be loaded in your RAM, which will be having some stack heap and so on, and private variables and so on. So this process, now if you have done the if you have done the work division and all those things, then what will happen is that you will be able to utilize all the 4 cores in this case. So that is what is the high level overview of using, what I meant by saying using the multiple cores that are available on your system. So, okay, so this was the high level overview, and you might think like how this is done, like how will multiple cores be utilized. So you have a single piece of code, right? And you want to run it on multiple cores. So what OpenMP will do is that it will spawn some threads, and each thread will be run on a separate code. So we'll see how this works, and we'll also see a bit detail about how what is thread and so on. But yeah, any questions up till now on what I explained so far? Let me go back to. Okay, no questions. Then okay, then uh, you can find the initial details. I mean, very comprehensive details actually about OpenMP on openmp.org. So you'll find multiple tutorials, news, and latest articles related to OpenMP on this website openmp.org. Okay, if there are no further questions, and yeah, by the way, if you want to install OpenMP, then I'll share the link. If you want to set up OpenMP, then I'll share the link for that also. Just give me a minute. Uh, I'll paste the link on the chat for those who haven't done yet. But yeah, I mean, it's a very simple step-by-step process. So I won't be covering this in the lecture, but yeah, you can set up offline, and we'll be discussing codes in the lecture. And yeah, if you have any doubts, then please feel free to post them on the group, or even during sessions, you can post your question in the chat. Okay, let me. Yeah, I'm unable to find the chat. Yeah, let me paste this in chat. Okay, now let me reshare. Okay, so that's the high level overview. Now let us move to the next slide. So yeah, as I told in the previous session, that the OpenMP is nothing but an directive-based API, and it's an extension to the current programming languages like C, C++, and Fortran. So you won't need a separate compiler as such for. I mean, you don't have a separate compiler as such for OpenMP, and it's just an extension to the current programming languages. So you can compile your code with OpenMP constructs using the same compiler, which is C++ compiler, and you can run it, but just you need to enable the extra flag. And the extra flag that I'm talking about right now is this FOpenMP flag. So yeah, so that is how we will run the OpenMP program. And one more good thing is that you won't need a separate infra as such, because nowadays the laptops or the systems that we have are having multiple cores by default. So that's a good thing, right? For let's say if you want to do GP programming using CUDA or OpenACC, then you might need a system which has NVIDIA GPU, or at least some GPU. But in this case, we are good, right? We have our system which already has multiple cores, so we don't need to worry about that. Yeah, so having been said that, yeah, so OpenMP specifies the standard for writing shared memory programs. And the standards are defined by the group of researchers and engineers who thought that if you want to do shared memory programming in, I mean, parallel programming in shared memory environments, then we should have a high level programming language, which is OpenMP is one of them. And yeah, the next thing is that OpenMP allows for incremental parallelization. So when I say incremental parallelization, what I mean is that you can write your code. I mean, you can parallelize your code step by step. That is, what you can do is, okay, let me go back to the board. Mm. Yeah. So, yeah, what I mean by incremental parallelization is that you have your some C++ or Fortran code, right? Now you might come on day one and you can parallelize some part of it. Let's say you parallelize it from line 10 to 15. You parallelize this portion of the code and you can leave it as it is, and your program will work in parallel. And even if there are other portions which you can parallelize, you can leave it them as it is for now. And after some days, you can come and you can parallelize even more chunk of your code and so on. So you can incrementally parallelize your code. You can add the pragmas. We'll see what pragmas we can. So you can add those constructs and you can go on parallelizing your code gradually. So that is what I mean by incremental parallelization. Yeah. So any questions up till now? Any questions? Okay. If there are no questions, then okay, then let us go ahead. So, uh, so the OpenMP is your direct. So OpenMP is the directive-based programming language. So your directive-based code can be compiled with a regular compiler as well. So what I'm trying to highlight in this point is that uh, first of all, your code will be the directive-based code. So you'll sorry, you'll be writing some directive a preprocessor directive in your code, which will allow you to parallelize your code. And the point is that you can compile that program even using normal compiler. So let us say that you have an OpenMP code and you have some file, let's say hello.cpp, which contains some OpenMP constructs. So even if you don't sorry, even if you don't add the uh, OpenMP that flag fopenmp, let's say you don't add this one. Sorry, but yeah, if even if you don't add this fopenmp flag, then also your sorry, your program should be able to compile. So even without this, your program should be able to compile. So you should so in general, we'll write the code in such a way that even if your program have the OpenMP constructs, your code will be able to, I mean, you'll be able to compile the code and you'll be able to run the serial code as well. And if you add the OpenMP flag and if you want to parallelize the code, then it will parallelize it. So yeah, so that's the thing. And yeah, let us move ahead. Any questions so far? Like we have covered a few points, and if you have any questions, then please speak up. Or you can even type on chat. Else we'll move on. Yeah, please go ahead. Yeah, please go ahead.
Yes. Okay. Thank you for having me here, sir. Just can we go over some like some use cases or some cases where we would want to parallelize over having linear code? No, I'm sorry, but if that is redundant.
No, so there might be some cases, right? Let's say your program is inherently serial. Uh, in those cases, you might not want to parallelize. So let me think about a case where let me think about a case where uh, parallelizing is redundant. Okay. I'm not sure, but let's say your task is such a way, I mean, is designed in such a way that there is a lot of dependency. So let me take an example here. Yeah, let me share it on whiteboard. Let us say that you have a simple for loop, right? You have a for loop, and in this for loop, uh, you have your computation in such a way that okay, I think somehow it is not okay. Yeah, sorry. I think yeah. Let us say that you have a for loop, and your computation is such that your current iteration, work in the current iteration, is dependent on the previous iteration. So let us say that you have something like this, right? In this case, you won't be able to parallelize this loop, right? Because in let us say that this E of I might E of I computation of E of I is dependent upon E of I minus 1. So you won't be able to do this, right? You can't just randomly assign, let's say, first 5 iterations to core 1, and so on, like second another 5 iterations to core 2, and so on. Because yeah, your computation will at the end become, I mean, the result that you want will not be consistent. So this is, I mean, if your code is not parallelizable, so the point that I was trying to highlight is that if your code is not uh, parallelizable, then you might need to look into some another way to parallelize it. But yeah, in this case, you might not parallelize your code. This case is this case is when you might face the incorrect result rather than I mean incorrect results by parallelizing it. So the thing is, parallelization comes afterwards. The first thing is correctness. So yeah, I hope I answered your question. So in that case, we will parallelize.
Thank you, sir.
Yeah. Any other questions? Okay, feel free to ask the questions, because otherwise this session will become very less interactive, and yeah, I won't be able to understand how much you are able to grasp. So yeah, please feel free to ask the questions if anything is unclear. Okay, then let us move ahead. So let us see how the parallelism works in OpenMP. Sorry. So in OpenMP, your OpenMP program will start with something called as master thread. And so your program execution begins with a master thread, and this master thread will spawn the parallel region. I mean, will spawn the team of threads when it hits the parallel region. And upon the completion of this parallel region, so you can see this blue thing. So this green thing denotes the serial region. So in serial region, there will be only one thread, which is our master thread. And as soon as it hits the parallel region, it will spawn the team of threads, and each thread will do its own work. So it will have its own. So I am assuming here that you know what the thread is, but yeah. So if you are unclear about it, then please ask about it. But yeah, so each thread will do its own work, and it might be executing on any core, and it will have its own stack and registers and program counter. And yeah, it will execute, and once the parallel region ends, all other thread except the master thread will be parked, and master thread will continue its execution ahead in the serial region. And again, when the parallel region is hit, it will spawn a team of threads and so on. So that is one thing. Apart from that, inside the parallel region itself, we can have another parallel region, which will form the nested parallel region. So when this thing happens, when we are in the nested parallel region, each thread within the parallel region will now become a master thread of its own team of threads. So let us say that in this case, this first thread, which was spawned in this parallel region as part of teams of thread, when it enters the nested parallel region, it will have its own team of threads, which is shown here by pink color, and it will be the master thread of its own team, and so on for each thread inside the nested parallel region. And the rules are same. When nested parallel region ends, the set of threads, I mean, the team of thread is parked, and other threads in the team are parked, and all other master threads survives, and they go ahead with the execution of the rest of the parallel region, and so on. So one thing here to note is that the master thread is the one which will be driving the entire, I mean, it will be running throughout the program. It will be there till the end of the program. And all other threads which are part of the team will be spawned and will be parked whenever the parallel region is encountered and the parallel region ends respectively. So yeah, I hope this is clear. Any questions on this diagram? This is an important diagram because there are many things here.
Josh, I have a question.
Yeah.
Suppose I think this is master slave architecture, the threads which are being created.
Yes.
Is there any way that through our program we can manage the slave threads, like their executions, scheduling? Can we manage it?
So I think scheduling you can't manage because OpenMP internally have some scheduling mechanism, but what is executed by which thread, you have some level of control. So we'll see that we have runtime routines to vary the thread ID of a particular thread. And using that thread ID, you can say that this thread should perform this task only, and so on. So you can have that level of control, but I don't think that we can have some scheduling level of control that we can do on these threads that are spawned.
Okay, okay.
Sir, is there
Yeah,
any
so-
way to
yeah.
properly determine like what number of threads would be ideal to deploy on a given system, because depending on the number of cores? Like, does OpenMP offer any constructs to for us to know that?
Okay. As far as I know, there is no such construct which tells based on your application. I mean, it's very application specific question, right? Like what will be, and as well as your hardware specific thing, like the amount of core that you have on your CPU. I mean, yeah, on your system. So yeah, I'm not sure. I mean, I don't know any such construct or any such runtime function that we have.
Okay, sir. Thank you.
But ideally, what you can do is you'll be knowing the the number of cores that you have on your system. So based on that, you can load balance it. And in general, for multi-core system, the number of cores are less. So you need to ideally, you need to ideally launch the thread based on the number of cores you have. Let's say you have 5 or 10 cores, then you'll be launching some hundreds of threads, but you won't be launching some tens of thousands of threads. You can launch tens of thousands of threads in case of GPU because that's ideal too, because GPU has thousands of cores. But yeah, in general, OpenMP won't restrict you even if you launch thousands of threads. But it's up to you based on your
Okay, sir.
application.
Thank you.
What exactly are threads and how are they related to the number of, let's say, cores in a system?
Okay, let me go back to my code. So you remember this diagram which I explained. So within
Yes.
this one, yeah, just let me explain it in a slightly better way. So you understood this till this point, right? That when we do ./a.out, your program will be loaded in the main memory or RAM, and it will become a process, right? It will become a process here, right? So what will happen? I mean, first of all, what is thread? So thread is nothing but a lightweight process, and how it works here is that when the let me move to sorry, the new slide. So when we reach the parallel region, what will happen is that so your code will have a serial region and a parallel region, right? Now, when you hit the parallel region, what will happen is that your process, which resides in your RAM, so this is so let's say your RAM, and this is your process. Your process which has OpenMP related code. For now, let us assume that it's OpenMP related code and it has some constructs, OpenMP constructs. What it will do is it will spawn some threads. So this is thread T1, this is thread T2, this is thread T3 within the same process. So this is the master thread. And this child threads or slave threads, whatever you would like to say, are T1, T2, T3 here. So they'll have its own stack, its own program counter, its own some registers and so on. But what will happen is that it will share most of the data, like code will be shared, heap will be shared, and so on. And the interesting thing here to note is that this threads that you spawn, right? So master thread might be running on some core C1. This thread T1 might be running on some core C2 and so on. So each thread will have some private copy of it. We'll have something in private and most of the thing in common, like code is there, heap is there, some files that are open, files that are open for this process that will also be shared among the threads. And and these threads might be running on the separate cores on your system. And that is how we'll be able to get the parallelism, right? So we basically spawn the threads, which are nothing but lightweight process. And those are executed on different cores as such. So I hope I made your point clear. I answered your question, or did I even confuse you? If there are any questions, please ask.
Yes, it's clear. Thank you.
Okay, so
Hello.
okay, if there are
Yeah, Josh, Harsh here.
yeah.
My question would be when designing an algorithm, should we go with multi-thread or multi-process kind of structure? And how would we determine that should we use thread or process? Because thread is basically a lightweight process, and there are many programming language. Many programming language gives us ability to use multi-processing and allocate a process pool. And
Yeah, so okay, let us look at it this way. So let me share it back. So let us say that your application itself is different, right? Let us say that you have a Word application, right? Now in this Word application, let's say you might need to do some task within it, right? Let's say autocorrect or something like spell check or something like that, right? Then that you can deploy it as part of a thread, because within the application you might need to do something. So code is same, right? Code is that of Word. Within that code, so code should be shared here, and that is what is the thing that I highlighted. Code is shared, as well as files, as well as few other things like heap, etc. are shared. But there is some functionality that you want to do in parallel. So for like autocorrect. So for that you might use threads. But let's say your application is completely different. Let's say you are using PowerPoint. Then you should have a separate process for it, right? You can't add this inside this. So I hope, this was quite a vague example, but I hope you got what I was saying.
yeah. So if the like each process is doing something different, we should go with multi-process. But if every process is doing the same thing, we should go with the threads.
Yeah.
Am I correct?
So yeah. So I think you got the gist of it. But yeah, so in general, I think I'll end with that. But yeah, let us move ahead.
Yeah.
Hello. So threads resides within core. So as I have 4 cores, but 8 threads, that means 2 core each thread, 2 thread
Yes.
each core. So my question is, who communicates with the global memory? Independently, each thread communicates directly with the global memory, or it's a core who communicates with the global memory, and somehow it is connected with thread, so it is being accessed
Yeah.
through some mechanism.
Yeah, I understood your question. So the global memory itself here, if you remember our shared memory architecture, right? Let me go back to that. Let me go back. Okay, if I have that, let me see. So in this case, in shared memory architecture, right? Our global memory is nothing but a RAM. I hope you can see this. So it's a RAM. So and if you see the global memory, inside this global memory, which is our RAM in this case, is our process, and threads are also within that process. And for this threads as well as process, there is some common memory which is called as heap. And this is all lying inside this RAM only. Please don't confuse it. But this heap is shared between, as I told before also, this heap is shared between these threads as well as the process, I mean, master thread as well as the child slave threads. So this is the place from where all the threads will read the common or global data. I hope I answered your question. And yeah, sorry, I was not able to hear you.
It's okay. I got it.
Okay. Yeah, so any other questions? Okay, then let us move ahead. Okay, so this is how the sorry parallelism in OpenMP works. So yeah, as I explained, in next slide we have this, like an OpenMP application begins with a single thread, which is master thread, as I explained, and as we encounter the parallel region, master thread will create the thread team, I mean team of threads, and at the end of the parallel region, this threads will be parked, and the master thread will continue its execution. And within the parallel region, we can have a nested parallel region in which each thread will become its master of its own team, and will continue the execution in the nested region as well. So I hope this part is clear, because we should be clear at this point, because once we start looking at the programs, we'll be using this terminology, master thread, child threads, or slave threads, and so on. So please, I mean, if you have any question here, then please ask. And if you don't have any question, then we can leave it. Okay, then if there are no questions, let us move ahead. So now let us look into the OpenMP constructs. So constructs are nothing but some high level the broad areas which are there in OpenMP. So there are two broad areas. One is the pragmas, and second is the runtime routines. So yeah, so pragma are basically helpful for parallelizing the section of code. So let me go back to the whiteboard. Okay, so as I explained, I think I have it here. No, okay, let me. Yeah, so you have this your code, right? And within this code, let's say you have some few lines of code that you want to parallelize, then you can use hash pragma OMP, and then something here. We'll see what is that thing. But what this essentially tells to the OpenMP part of the compiler is that sorry, is that whatever comes after this hash pragma OMP, you need to send this part to the OpenMP part of the compiler. And basically what it will do is that it will parallelize this part of the code. So basically, pragmas are the thing that we will be using for parallelization. And yeah, so let us go back. So yeah, so pragma, after hash pragma OMP, there are two things. One is directive and another is clauses. So directive can have multiple types, like parallel for, section, single, master, and we'll be seeing all these types in our future sessions. But yeah, these are the directives, and for each directive, let's say a parallel directive, if you pick one directive, then you can have multiple clause for this directive, like parallel for is like no, sorry, not parallel for, but parallel, then you might need to specify something like number of threads and so on. So you can specify those things and a clause. So yeah, so these are the two parts of the hash pragma OMP. One is direct, another is clause. And this thing basically directs your OpenMP part of the compiler. I mean, it will be sent to the OpenMP part of the compiler, and it will be used for parallelizing the serial portion of the code. Any question on pragmas? We'll see the practical example today itself, but any questions?
So there are these 12 directives only, or the list is includes more?
Sorry, I didn't get your question. Can you repeat?
In the last point, the directives, there are 12 directives you have written. Parallel for, sections, single, master, critical, flush, ordered, and atomic.
Yeah, so these are
So,
not the only ones.
is this
There
the
are more.
only directives, or there are more like
There
this?
are more actually. I've just listed a few of them.
Okay. Thanks.
Okay.
Just this is Harsha.
Yeah.
Essentially, this pragma directive, does it always create a critical section, or
No, it won't create a critical section. What essentially it will do is, okay, it will, I mean, it will not definitely create a critical section. It will just, based on the directive, it will do some work. So if you write hash pragma OMP4, we'll come to this thing again. But yeah, if you write hash pragma OMP4, it will just parallelize the loop. I mean, hash pragma OMP parallel for, it will parallelize your loop and so on. But yeah, it doesn't ensure any synchronization or anything. We'll see where the synchronization is coming into your picture here, but yeah, by default it doesn't do anything.
yeah. Thank you.
Okay, any other questions?
What exactly are these directives, like parallel for parallel?
So, so these directives are, what I can say is that these are the signal for the compilers that whatever is coming next, you have to do some operation in it. So let us say hash pragma OMP parallel, it instructs a compiler, OpenMP part of the compiler. So OpenMP part of the compiler that you have to do, I mean, you have to handle the actually we'll see this later also, but you have to handle the structured block of code that is coming next in a particular way. That is what it tells. So that is what is the directive. What is the that is the function of the directive. And clause is basically trying to add some more information to this directive. That is what I can see. I hope I answered your question.
Yes. Okay. Thank you.
Okay, so if there are no further questions, then let us move ahead. So this is the overview of what are pragmas, but yeah, we'll see the practical example today itself. And then comes the second part of our constructs, which is runtime routines. And OpenMP has a lot of runtime routines. I've just listed few of them here, but just to get started with it, just get our hands dirty. But there are a lot of runtime routines within OpenMP, and we'll see them as we proceed with this course. But what exactly are these runtime routines? So what it is like basically when you run your parallel program or when you are in parallel environment, you might to query a few things, right? You might to get some information, send some information, I mean, set some information or something like that, right? So that you can do it using runtime routines, and it helps you manage your program in parallel mode, basically. So what I'm trying to say here is that you might want to set and retrieve some information. So let us say that you are in the parallel region of the code, right? We saw in the previous slides, right? There is this parallel region of code. You are, let's say your execution is currently happening within this parallel region of the code. And let's say you want to query the number of threads that are there that are currently executing. So that information you can retrieve using this runtime routine known as OpenMP get num threads. So this is the routine which tells us as a programmer that what are the number of threads that are there in the current environment, current parallel region. Similarly, set num threads will be used to query the number of threads, number of threads with which you want to execute your parallel region, and so on. So yeah, we'll see this all of them as we go ahead in our course. But yeah, any questions up till now? Okay, I think let us proceed with our first HelloWorld program. I think these things will be clear with that. I can explain them better with that code. So let me share code now. Okay, I'm hoping that you are able to see this code on the screen where I'm projecting the code. So if you see this code, first few lines of the code are, we are just importing the library, but the only change, so these are the standard C libraries and C++ libraries. But here you can see that we are including something called as OpenMP.h library. So basically this is a header file for OpenMP, and it contains several directives, variables, functions, and so on, few other things also. And so we are basically including that part using this OpenMP.h. And yeah, this then there is this hello function which we will see later. So you can see here that we are using some runtime routines here. We'll see what they are and how they are working here. So, but yeah, first let us come to the main part of this program. So in this main program, we have this argc and argv, which are nothing but the runtime arguments that we are passing to our function, our program. So argc will contain the total number of arguments that we have, and argv will contain all those runtime arguments. So first one is the name of the program, and rest are the ones that we are passing to our program runtime. So yeah, and here we are defining the thread count, and which for now I have kept 1. And then what we are doing is, if we have more than one argument, that is apart from the program name, if we are getting something, then we are setting the thread count based on our second runtime argument that we are getting. And so basically this runtime argument will be in form of string, which is nothing but a character array. So we'll convert that string into integer, basically string string to long, using this function str to L, which is standard C library function. And we'll be passing the first argv of 1, which is our second argument, because first argument is the program name of the program, and second one is the one which we are passing. So we'll take that and we'll convert it to base 10, basically base 10. And this null says that we'll go till we hit the null character within that string or the character array. So basically we'll convert that string to integer here, and we'll give it to thread count. So thread count will contain the number of threads that we want. And in else part, we'll be throwing some error that please enter the second argument to the command line so that we can set the thread count. Basically, we can set the number of threads with which we want to launch the program. Then comes this part that we were talking. This is pragma. So hash pragma OMP parallel. And then we are setting num threads. So can anyone tell what is this? What is this parallel and what is num thread in this? Can you name this?
Parallel is the directive, num threads, and these are like the clauses.
Yeah. So I hope you're getting it, like as we saw in our theory slides, like this is our standard syntax, hash pragma OMP. And then whatever comes next is our directive. And after that, this is clause. And what this entire thing is telling is that whatever comes after hash pragma OMP, please send it to OpenMP part of the compiler. And whatever, so it will be sent to the OpenMP part. And based on that, the structured block, so I've written it here also, structured block, which comes next will be parallelized or whatever the directive is. So here it's parallel. So structured block, which is after this hash pragma OMP parallel num threads, will be executed in parallel because we are writing parallel directive here. And what num thread says that we want to execute this structured block with thread count number of threads. And here the thread count is given at runtime, right? Here it is passed at runtime. So I hope you are getting this. Any questions up till now?
Just I have a question. This is Harsha again.
Yeah.
I essentially in C program, if you create threads, it creates a thread, right? Not only folks create processes. Like that.
Yeah. So
here we create only threads, right? Not the processes.
No. Here we are creating just threads.
Okay. The second question is does this OpenMP can be installed and we can write program in Mac OS? That is also possible, right?
Yeah, I think it should be possible. I haven't tried personally, but yeah, it should be possible.
Okay, thank you.
As long as you have extension to the GCC or G++ compiler in that, you will be good.
Okay, thank you.
Which I think you should do on Mac also.
Okay.
Any other questions? Okay, so I have a question then. What is the structured block? I'm quite speaking about it, right? The structured block and so on. Like what exactly is the structured block? Does anyone know? Do anyone have any
This is like a function.
context about it?
This is like a function which can be called in parallel.
The structured part is basically the block of code which would be executed in parallel. So for example, we have executed hello here, right? So I think because we have passed the parallel directive, the hello function should get executed like in parallel based on the number of threads.
Yeah, I'll say what you are saying is correct, but there is one part that is missing within this. So you can't say anything as structured block unless you have one or two conditions that are met.
You have defined hello as int time size open get num thread and int tid open get thread number. So this particular block will execute this hello, and with it will get the threads on which this particular function is being executed.
Yeah, that is quite correct. But again, my question is like,
Is it exactly like this block of codes, okay, is going to share the memory? It is the multi-core architecture you have discussed where the shared memory is being done. I think this is what it is.
Yeah, that is also correct. It is a shared memory system. So this hello, so we'll be spawning the threads as I discussed, right? We'll be spawning the threads here, and each thread will be executing this hello part of the code one
Can you,
separate course.
yeah, can you give
So
us a comment? What is that you want to know? I mean, want us to tell you. Can you give some?
yeah, so I'll tell you actually what I'm trying to derive here. So
Sir, this
when I
whatever in curly brace, sorry, whatever in curly braces, this block, if there were multiple statements, then that would have happened uh, sequentially. But overall, all these should occur parallelly. Is it?
okay, so okay, now
Yes,
let
sir.
us combine everything that we actually your comments. I'm trying to merge them and trying to draw some conclusion out of it. So let me share. So yeah, so what I'm trying to say here is that this is some structured block of code, right? We have within this curly braces, right? Why am I saying that it is a structured block of code? So first of all, let us see this, right? Let's say if I had something apart from hello, then let's say something like this, then each thread T1, T2, T3 might have executed it sequentially, all these three, but each thread is executing in parallel, right? So that is one thing that we should be clear about. Second thing is the definition of structured block of code, right? So when I say structured block of code, one thing should be very clear that whatever is there within this curly braces only have one entry point and one exit point. So you should be enter it from here only at one place only, and exit should be also from one place. It should not happen that you end up exiting in between this. So let's say you can't write some go-to statement such that you jump to some line of code that is outside this structured block. So this block basically. So that is what is the structured block of code. I hope this is clear. Any questions?
In a way, you mean to say that they are atomic, right? All these instructions are
No,
atomic.
not atomic, not atomic. So yeah, kind of see each thread will be executing it, but it is not that it can jump outside this block of code. It has to finish all these three.
That is what I meant. Suppose if
Okay.
we
Yeah,
if we
if that's
consider
the
this if we
yeah.
consider these three functions as transactions in DBMS aspect, all the transactions should be in a will be executed as atomic unit, right? All of them we have to execute.
Yeah.
Mhm. Okay.
Yeah, in some sense you can say that. Yeah, but we'll come to it. So
Yeah,
these
yeah.
functions might be
If the
modifying something,
just
some variables. Yeah, sorry.
mm,
Sorry, please go
if,
ahead.
if the control goes out of the block, so the control won't come back again. It is like some kind of exit statement. If there is is it right?
Yeah, so yeah, kind of that. So the point that I was trying to say is that control, I mean, that should be just one entry and exit. That is what I was trying
Yes,
to
yes,
say.
yes, sir.
So Josh,
It
if I'm
doesn't
having
have.
some program, hello.
Yeah, please go ahead.
Yeah. So if I'm having some program, let's say hello function, and based on the result of hello function, I'm doing two separate things on the foo function. That won't work here because the foo function will have like multiple exit points based on the input of hello. So
I think
that can't be included in structured. Is that correct?
yeah, I think we are getting like confused here, but okay, let me clarify this. So there is this hello function, right? It might do something, and its result might be also used in the next function, let's say foo, as long as they are let's say you might define something also here. Let's say you are defining some variable here, right? And that variable you can pass it. Actually, you can pass it. So these will be thread private variable. We'll see what is that.
Mm-hmm.
So we can do that. But what I'm saying is that you should not. I mean, you can't say if it as structured block if you are going outside of. I mean, going outside in the sense that you're going to some line which is outside this curly braces. So that is what I was meaning. So you can just search for the definition or look into the books for the definition of structured block. So that is what it is. These two conditions should be one entry connects.
So,
I
sir,
hope this is clear.
in case it is not a structured block, how will this program will know? Like it can be inside something somewhere, but
I
still
think
we may be.
Yeah, please finish. Sorry, I was.
Sorry, like I mean, so if it is exiting, that too, it will happen inside function, right? But by that time, we would have already given it to the process. So how will that it manage if the programmer does not is not careful with the structured part?
Yeah, this is good question. Actually, I think OpenMP compiler should by default, I mean, OpenMP part of the compiler should by default error out in that case. But I think we should check this once. What happens? Like, let's say if we do some juggling with it, like let's say we write some code or something, then what happens? We can try. Basically, you can take it as a homework. You can try what happens if you write a go-to statement within this structured block and you try to jump to some another line. What happens? You can check that. You can take it as a homework and try what happens. I think most probably OpenMP will error out here, but yeah, please check. Okay, so let us move back to our slides. I mean, sorry, not slides, but our program. Okay, so we are clear, right? That this is this is directive and this is clause. And we have this structured block. Essentially, what this tells is that whatever is coming after this hash pragma MP, you have to execute it in parallel. We are directing it to OpenMP portion of the compiler and saying it that please execute this in parallel with thread count number of threads. And within this hello function, let us now look into the hello function. What we are doing is we are using this runtime libraries that we saw, right? Basically, we are saying what is OMP. I mean, we are basically calling OMP get num threads and OMP get thread num. So OMP get num threads will give the number of threads that are there in the parallel region. So let me go back. Okay, I hope you're getting it. So so this is the parallel region now, right? This hello function is an entire one parallel region. And how many threads are executing this parallel region is what we want to query. So we want to get some information. And the natural way to get this information is using this runtime routines. And the OMP get num threads is one of the routine which we will be using to get the number of threads executing inside this parallel region. Second is OpenMP get thread num. So this one will tell the thread ID of a particular thread. So let's say thread. So we have 5 threads, right? So OpenMP get num thread will return 5, and OpenMP get thread num based on which thread it is executing, it will return the thread ID, and it will start from I think 0. So it should give 0, 1, 2, 3, 4. So each thread will get its own ID, and it will be stored in TID, thread ID basically. And then what we are doing is we are essentially printing this thread ID and the team size, basically the size of the team or the team of threads. And we are printing that information and then we are exiting. So as per our diagram that we saw in the start of the lecture, right? So this portion is a serial portion. And in this portion, only master thread is currently executing. When we hit this part, this thing, our parallel region begins here, right? This part here. When the parallel region begins, the master thread will spawn the team of threads. And basically here, this entire portion will be executed in parallel by team of threads. And once that is executed, once the result is computed, everything, and then when we end here, the team of threads, I mean the threads within the team will be parked and only the master thread will resume the execution from here. This is again a serial portion. And yeah, this return 0 will be again executed by just master thread and will end our program here. So Yeah, I hope this is clear. Any questions up till now? So this is the entire basic hello world. We'll execute this also on our system right now. But any questions so far? Questions?
Excuse me, sir. Am I audible?
Yeah.
Sir, I had a question that you said the execution should never go outside the outside the structured block. That statement I didn't understand quite well, because while calling a function, our execution does go out of the basic structured block. So is that allowed?
So, okay, I think I'm lacking clarity here, but uh, okay, let me explain it in this way. So
Okay.
this hello function,
Yes.
consider this one, right? This statement, this
Mhm.
set of statements. Is it doing something which is leading to your program control going out of the parallel region and jumping into the serial region? So let us say, are we doing anything here which is causing our program control to go to this portion of the code or this portion of the code? Are we doing anything like that?
No.
So that is what is it. It is like
Oh, I
this hello
understand.
part. Yeah, so this hello part is a function call. So think about it in this way. When this program will be compiled and converted to assembly, this hello will be having this set of instructions which will be replaced in as part of this, right? And those will be there in as part of this block only,
Yeah,
right?
yeah. So you should
I
you
hope I
yeah. Now I get it. That there is a chunk of code that you have defined is serial, and a chunk of code that you have defined is parallel. And in the basic in the structured block, you should only access those regions which are parallelized or you have considered as parallel, and never enter the serial region.
yes. So
Okay,
basically
great.
within this function.
Got it.
Yeah, I
Thank you.
think you have now understood. Yeah. Any questions for that? Else we'll just try running this code and see the output. We'll just play around with this code now. Okay, let us now try running this code. So let us run this using our standard, as I told, right? G++ compiler. I'm using WAL for warning, so you can remove this. So WAL will give all the warnings that are given by the compiler. FOpenMP flag is very much needed because we have this pragma based code, right? So we'll need this FOpenMP flag. I'm saying -o hello, which is I want to name the output file or the binary file as hello, and then we are giving the name of this program, which is hello underscore openmp.cpp. Now I'm running this program and it should compile it. I mean, I'm compiling this program, not running. So now this program is compiled and binary is generated, and the name of binary would be ./hello. So now binary is ready, and now we can run this program. So when I say we'll run this program, now we'll go
sorry to
on the
interrupt.
RAM and yeah.
We can see only the code. Are you compiling and running the program? We cannot see.
Yeah, sorry. I think I need to share. Sorry for that. Okay, let me share that also. I'm really sorry. Actually, I forgot to share that screen.
No problem.
Is it visible now?
Yes, yes.
So sorry for that. So what we have done so far is that we have compiled this code using G++ compiler by adding this flag -f openmp, and we have named the output binary file as hello. And with this compilation is done. So this portion is the compilation and our binary is generated, which is ./hello. Now we'll run this binary and it says that you should give the second argument, right? Because we aren't providing any argument. And as you remember from our code, we should provide at least one argument apart from the name of the program. So now let us specify some argument. Let's say I want to run this program with 5 threads. So second argument is the thread count, right? If you remember, it's a thread count that we are passing and we are converting it to string to integer, and this integer is the thread count. So yeah, it gives some output. So did you notice anything here? Sorry, any observations with this output? Did you notice anything?
I think only 2 threads are
So
running.
each thread was trying to get the access of the output, and that's why we have
Yeah. Yeah, so all 5 threads executed. So I want to first of all convince each and every one of you that all 5 threads are actually executing. So let me execute it once more. So the difference here is that here the output is jumbled because all the threads are competing for the standard output, that is the console output, and that's why it is giving the jumbled output here. And here also it might well have happened, but luckily here it is not as jumbled as this. But if you can see here even that the order is not still correct, like thread 1 printed first, then thread 0, then thread 3, and so on. So this can happen, right? Because each thread, as we saw, right, each thread might be executed on different core, and each core is executing the piece of code in parallel. So, and the standard output is something that is common resource. So they are competing for standard output, and they are dumping their output in them. So this might very well happen. So this jumbling of output might very well happen, as well as ordering might also be different for each. Ordering might be also different. So it is not the case that it will always print thread number 0, then thread number 1, and so on. If you want such output, then you can get it, but you will need to write extra code for it, and basically you will need to have some synchronization, something like that. But yeah, I hope this point is clear. Any questions so far?
A silly question, but what does this dash wall in the first line of the code?
Sorry, but yeah, that is for enabling warning. So if there are any warnings that your compiler is giving, then it will basically we are enabling all the warnings to be printed by the compiler. That is, you can just eliminate this also, it will still work. So I'll show you. It still works, right?
Okay.
The only important thing is this app OpenMP. Even you can remove this part also.
Then the output will be at the ./out.
Yeah.
Yeah.
Then you need to execute using ./8.
Okay.
Okay, any questions up till now? Okay, if you have no questions, then I'll ask a few questions. Then let me share my screen again. What will happen if I do this now? Okay, I've used this runtime library, runtime function routine, right? OMP set num threads. I've set 10 threads, but I'm still passing the thread count here using this one. So now how many number of threads will execute this this hello portion of the program? Thread count number of threads or 10 threads? What do you think?
So it should execute thread count number of threads. That's 1.
Okay, any other suggestions?
With this, it should execute thread count number of threads.
Okay, then yeah. Okay, anyone wants to go with that 10 threads one? 10 thread suggestion.
It's a kind of global setting.
So I think that num threads 10 would only execute if we do not pass the thread count, so it would switch to the default. But if we are passing the thread count, it should only execute the thread count.
Yeah, I think you people are correct here. Let me try running this one also. So if I recompile and rerun this, right, it will still run with 5 threads only. So this whatever we define in the clause, the point that I was trying to derive is that whatever we define in the clause takes the precedence here. So it is printing still, it is still executing with 5 threads because this has high precedence. But let us say that now if I remove this, right, just hash pragma MP parallel, and I specify 10. Now, what do you think? It will execute with 10 threads or random number of threads?
So now it should
10 thread.
Yeah. Let us run this now. Okay. Yeah, even if I'm now passing 5, it is executing with 10 threads. Okay, so that is one thing. Now let us again go back to the code. Okay, now let us is this okay, and now let us try something else. What can we do with this program? Yeah, let us do this thing. What if I do this? Now, how many number of threads do you think? I mean, how many number of threads will execute the hello now? Any suggestions?
So now it should execute like whatever OpenMP defined by default in the global setting.
Yeah, that is correct. But any suggestions on what OpenMP defines as part of its global settings?
4. Maybe number of cores.
I think 1 should only go for 1.
Okay, any other suggestions? 4, 1, any
4
other apart
default.
from 4 and 1?
Threads available in the system that will be displayed.
Okay, okay. I think I've got many suggestions. Let us try running this one. We can see what actually it gives. So it ran it with 4 threads. And why 4 threads? Because my system is 4 core system. So it ran it with 4 threads. So when we don't define any number of threads, then what OpenMP by default will do is that it will create as many number of threads as the number of cores. So that is what is the default behavior. So I hope you got this point. Okay, now let us move to our code again.
So can we use this default numthreads count as a reliable metric for getting the number of cores in a system?
Maybe, but I think there might be some. I'm not sure, but I think there might be some another way also, which you can reliably, I mean, foolproof way, such that you can find the number of cores. I mean, there are also Linux functions that you can run on your command line using which you can get the number of cores that are there on your CPU. I mean, on your system.
Okay, so thank you.
So, yeah, there are several ways in which you can get the number of cores. Even better than
so-
this. That is what I'm trying to say.
Yeah, so by default, your system has 4 threads. Okay, so when we say go with 10 threads, would it be like 4 threads will be running in parallel at the same time, and the rest of the threads will be waiting for their turn?
Yeah, so what happens is that at the time, if you have 4 cores, then I think you have 4 hardware threads, right? So at each
Yeah.
time, only 4 threads are actively running at any particular point in time. The rest all threads are in some sense parked, or I mean, they are just waiting for that thread. So that is the way you can interpret. So yeah, you are
So-
correct in that sense.
So main thread would wait for every thread to finish, or we can define like okay, if half of the thread or some of the threads are finished, you can like start with other instructions which are not dependent on the result of threads.
Yeah, so this is actually a good point. So let us go back to this slide. So when the parallel region ends, so what you are trying to suggest here is that when parallel region ends, then will the master thread continue or it will wait for other threads? So in this case, in case of OpenMP, it will wait for other threads. So until and unless these three threads have finished execution, the parallel region master thread won't proceed further, and it will wait for the threads to finish. So there is an implicit barrier across the end of the parallel region. Or
Okay.
in other
And
words, there is an implicit
when we say master thread, if the parallel threads are running on full hardware, like number of cores, where would master thread be? It will be just waiting outside, or we
No,
can
no.
have master thread report us on periodically, like how many number of threads have run and how many are remaining.
So no, I think master thread is also part of that the thread team, as I told earlier, right? It is part of the thread team, and it is one of that thread in that team. So it is there executing a parallel region.
Okay, so if I'm executing, like if I'm saying set number of threads 10, in actual reality, there will be 11 thread and 11th would be our master thread.
No, no, no. So there will be 10 threads. So okay, I think I'm not 100% sure here, but if you are telling that there are 10 threads, then there will be 1 plus 9. There will be one master thread, apart from which there will be 9 threads that master thread will spawn, and in total it will be 10.
Okay.
But I need to check this
Okay.
once. I'm not 100% sure about this. But yeah,
Okay.
this is the I think this is the most probable thing that will happen. Which is also confirmed by our diagram, right? So this diagram I've taken from OpenMP website only. So this diagram says that the master thread is part of the parallel region, so it is executing within the parallel region as well.
Just I am little bit confused about this core and the thread concept. You just said that if I am having a 4 core, then it will print if I am not directing anything about the number of threads which needs to be printed. So I just ran a simple code of HelloWorld with hash open pragma. In place of 4, it is printing 8 hello worlds. I'm having 4 cores but 8 threads in that.
Yeah, so let me clarify this. So I think if I got your question correctly, then what you are trying to say here is that you are running your program with 8 threads, right? But since you have only 4 cores, it should print only 4 times. But that is not correct, right? Even if you have 4 cores and if you have 100 threads, it will print hello world 100 times only. Because even if you have only 4 cores, what the scheduling algorithm will do is it will schedule some threads for one particular core and some another threads for other core and so on. So let's say you have 10 threads, then 3 will be scheduled for this core, 3 will be scheduled for this core, similarly 3 here and maybe 4 here. No, sorry, not 4, but let's say 1 here. I don't know what's the scheduling algorithm. That is something that OpenMP does it internally. But yeah, so that is what it is. So even if you run with 100 threads, it will print 100 times only, not just 4. Even if you have lesser cores than the number of threads. So I hope that was your question. I answered.
So if I am having 8 threads, it will at max print 8 hello worlds, not more than that. If I give directive for printing for 10 threads, then it will not print 10, it will print only 8.
No, sorry, can you repeat your question? What you were trying to say?
Suppose I am having only 8 threads in my system. So, and I am giving directive to print it for 10 times, 10 threads. So it will print only 8 times or it will print for the whole 10 times?
It will print 10 times if you have if you are spawning 10 threads. That is for sure. So if you are specifying thread count as 10, then it will print 10 times only.
Okay.
Irrespective of the number of hardware core that you have. Even if you have 4 cores, and if you are giving thread count 10, then it will print 10 times.
Okay, it will wait for one round and then it for the remaining it will use that same hardware to print another 2 ones.
Yes, yes. So this hardware resource, which is 4 cores, will be shared between 10 threads.
10 threads. Okay, okay. Got it. Thank you.
Okay. Okay, let me go back. Okay, I think we are reaching end of time. Any questions that you have? I'll continue from, we can continue from here from next time. But yeah, any questions that you have? We have 2 more minutes, so I'll like to take any questions if there are any, rather than going ahead. I'll wait for 2-3 minutes and pick up questions if there are any. So please try this code. Set up OpenMP, try running this code with this code. So there are some modifications that I made, but there are a few others also that you can make. So there are few things that you can try. Like you can try running this code without giving f OpenMP flag and see what happens. You can try a few things also, a few other things also. So please feel free to try running this code by tweaking some lines and so on. So please do that. Yeah, please go ahead with it.
Yeah. Hi, sir. Could you please share the resources covered today? I'll just like go over them a little later. I can't go through with the exercise right now. I have like another time commitment right after this. So,
Okay, I'll share the code as well as the slides for today in the Excel, that Google Sheet.
all right. Thank you so much.
Yeah, thanks.
Josh, if you can share the slides that you are creating. You're using some whiteboard, right?
Yeah, this one. Okay, I can. I'll see if I can share that, but I'm just using it for rough for
Yeah,
fun,
yeah.
not.
Mhm.
I'll see if I can share that also.
Okay. Thank you. You are very patient. Whatever the question we ask you, you are answering them. Thank you.
Yeah, thanks. Okay. Any questions? I'll wait for 1 or 2 minutes. We can call it a meeting and yeah. Okay, if there are no questions, then we can call it a meeting. See you all on next Saturday at 5 p.m. Bye.